For the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the solution process. In our last lesson, we learned about endothermic processes, and we discussed the term heat of solution. We learned that heat of solution is the amount of heat energy absorbed or released when 1 mole of a substance enters solution. We also learned that the first 2 steps of the solution process are endothermic processes. We finished our lesson by talking about an experiment which combined ammonium nitrate crystal with water to realize what an endothermic solution process is. In today's lesson, we will explain how heat of solution is influenced by the interparticle forces of attraction. We will focus on exothermic processes in this lesson as opposed to endothermic processes. We will also apply the concept of heat of solution to a solution of sodium hydroxide crystal. Students, I am ready to get started if you are. In the last few lessons, we have been learning about the solution process. Please draw a diagram involving the 3 steps of the solution process. Also, please state whether each step is endothermic or exothermic and why. You may begin now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, everyone. I'm sure we have some great artists in this classroom. Let us go over the solution process together. In the first step of this process, the solvent particles expand to make room for the solute particles. In the second step, the solute particles also expand so that they can fit into the space between the solvent particles. Both of these processes are endothermic because they require the absorption of heat energy in order to take place. In the third and final step, the solute particles mix with the solvent particles. This step can be either endothermic or exothermic, depending on whether heat energy is absorbed or released as a result of the solution being produced. In the final step of the solution process, each solute particle becomes surrounded by a layer or cage of solvent molecules. This is because they are attracted to one another by intermolecular forces. As we just discussed, this final step can be either endothermic or exothermic. This step is referred to as solvation. It can also be referred to as hydration if the solvent being used is water. Students, let us discuss this formula. The heat of solution is equal to the first change in heat energy, or the first step of the solution process, plus the second change in heat energy, or the second step of the process, plus the third change in heat energy, or the third step of the process. The first and second changes in heat energy are enthalpies required to separate solvent molecules and solute particles, respectively. Students, I am sure you remember that an enthalpy is a measure of the total energy of a thermodynamic system. The change in heat energy 3 is the enthalpy of solvation. If the solute-solvent attraction is stronger than both the solvent-solvent and the solute-solute attraction, then the solution will be exothermic. This situation is referred to as being favorable. If the solute-solvent interaction is weaker than the solvent-solvent and solute-solute interactions, then the process is endothermic. The combination of the three steps of the solution process is equal to the change in the hydration energy of the particles as well as their lattice energy in the case of solid-liquid solution. Students, what is the relationship between the terms solvation and hydration?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Solvation and hydration can refer to the same process if the solvent used in the solution process is water. If the solvent is not water, then the term solvation is used to describe the process in which solvent molecules surround the solute particles. In our last lesson, we discussed an experiment that involves a solution of ammonium nitrate crystal. We observe that the solution produced was endothermic because the temperature of the surroundings decreased, suggesting an absorption of heat energy from the surroundings, as opposed to a release of it. Let us go through that experiment again. However, this time we will use sodium hydroxide crystal rather than ammonium nitrate crystal. We begin by pouring 50 milliliters of water into an Erlenmeyer flask. We place a thermometer into the flask so we can measure and record the initial temperature of the water. Once the temperature is recorded, 4 grams of sodium hydroxide pellets can be added. Place a cork in the top of the flask, along with the thermometer as shown in this animation. Then gently swirl the flask to stir the contents and record the highest temperature reading. For the solution of sodium hydroxide crystal and water, we can tell that the solute-solvent attraction is stronger than the solvent-solvent and solute-solute attractions. This is because we get an exothermic reaction. The temperature of the solution increases because the extra energy is given off as heat. In today's lesson, we reviewed the solution process and discussed each step in relation to its change in heat energy. We learned that exothermic processes are referred to as being favorable. This is because of the favorable attraction between the solute and solvent particles. We also looked at the solution process of sodium hydroxide and determined that it produces an exothermic reaction. It is exothermic because heat energy is released. This is all for today's lesson. Until next time, thank you, teacher. Thank you, students.